Okay, I'd like to start my lecture. The title is a Boring Heat Transfer, study of the micro-diamond coating surface using the underwater explosion shock wave method. I'm Shuichi Torii, Kumamoto University, Japan. The first, I'd like to show the abstract. The full boring heat transfer experiment performed on the diamond particle coating heating surface, DPC heating surface, and the no coating smooth surface on the copper substrate. Here, the DPC heating surface is fabricated with the aid of underwater explosion shock wave. The experimenter conducted on the substrate surface of the 50 millimeter square meter is using distilled water as a working fluid. The substrate is fixed the heating block, which is embedded of the ceramic carpet heater and 1,500 watt. The influence on the pool boring heat transfer experimental is the study of the range of the surface reference value of the particle coated heating surface at the atmosphere pressures. The obtained result of DPC surface compared with that of the smooth bare copper surface. The remarkable enhancement critical heat flux (CFH) at the lower superheat is observed on the DPC surface. DPC surface is found to be effective increasing the nucleate boring of the CHF. The first, I will show the background, the purpose of the research. The boring transport phenomenon is an effective heat transfer effect. During phenomenon in the many industrial products, namely air conditioner, the boiler. In order to produce the performance of the digital equipment, but during many problem, integrated circuit heat generation problem, the improve effect of the heat exchanger. We need to enhance heat transfer performance. There are many methods to promoting in the boring heat transfer. The four types. This is the employment of the non-food. Obviously, the superheating and oriented heat flux. You can see that the heat flux is the substance increasing with increasing boring fraction, boring rate. The right figure of the different surface, rough surface is the smooth surface. Finally, the heat flux is enhanced. Next slide, if you employ the binary mixture media. If you employ the binary liquid media, this is a solid surface, and to the binary, the liquid problem is combined. The heat flux is the substance increasing. Last one, ultrasonic radiation. The surface, the artificial is like this to enhance the promoting of the boiling. This is the mechanism of the boiling. The left hand side, the very smooth surface, but there may be a crack, like a dimple. This is the trigger of the promote the boiling, like a bubble. There is right side artificial surface. Artificial surface, so-called the microfabricated heating surface. The bubble is a make and to enhance the presence of the bubble. To enhance the bubbling from the artificial surface is a boring heat transfer is promoted. So now I implement the the diamond coating. But this, the two coated diamond particle on the heating surface. We know that the characteristic diamond is high thermal conductivity. Ablation is the resistance. So left side, as mentioned previously, of the smooth surface, but there is many the small dimple. This is the promote is a bubble. The right side, the very small particle. This is a diamond. The also micro size. This particle is installed the surface. There may be artificial dimple like this. And the diamond is a high thermal conductivity of the bubbling is promoted with the increasing time. So the purpose of the present study to develop the method of fabrication diamond composite diamond metal. So the first, we fabricate diamond particle coated heating surface by underwater shockwave. In particular, we consider the effect of the diamond particle coating on the boiling heat transfer. In Kumamoto University, there are many of the unique shockwave condensed material research center. This center is so unique because it can employ diamond. This is an underwater shockwave tank. We employed underwater shockwave tank. This is a water tank, and this is a copper block. This surface is a very small diamond is collected, and this is a electric detonation, the explosive, the particle push install the surface. Basic base material is a copper block, length 50 millimeter, wide 50 millimeter, height 40 millimeter. Microstructure. This is the diamond particle size. Particle size is the diameter is 8 to 20 micrometer. Explosive is a SEP. Experimental condition is the distance of the surface is the explosive. The 10 millimeter, 20 millimeter, 30 millimeter. This is one of the result. This is artificial surface. This we employ the microscope. The left side optical microscope. Right hand side electric microscope. You can see that diamond particle attached. The install is without a gap. Now that we employed DPC heating surface. The D is a parameter to construct the surface. D is a 10 millimeter, 20 millimeter, 30 millimeter, and smooth surface. And I cut of the cross section of the surface. You can see that the Germanium is a dimple. And this is a diamond. This is a copper. The first, I'd like to show the experimental setup and method. This is a water tank. And this is the artificial surface. Artificial surface heating of the heat block. And this is a thermocouple to measure the heat flux and temperature distribution. And finally, it's made is a wall surface, temperature, and heat flux. Experiment is as follows. First, added distilled water to container and heat with the accelerate the heater with 40 minutes. Boil the bubble is generated from the DPC heating surface by the heating the copper block with the heater. confirm the steady state with data log and measure the inner temperature of the kappa block using some couple, like this point. And this is the deviation of the heat transfer coefficient. This is the definition of the heat flux, like this. How do you estimate of the heating wall at this point? First, we measure the three different three different the wall using three different sum couple. After that, this is the definition of the heating surface temperature, like this. And this is the definition of the superheat, the degree of the superheat, like this. Finally, we estimate heat transfer coefficient. This is the definition of heat transfer coefficient. This is a result of the heat flux versus the degree of the superheat. Abscissor is the degree of the superheat. Ordinate heat flux. The different symbol is a different surface, artificial surface, smooth surface here. The result here. And this is a smooth surface. The three different surfaces, three different surfaces is just B is different. The values, the narrow, the area is D equal 10 millimeter. This is the heat flux. And this point, critical heat flux. There are different critical heat flux. Point, this point, and this point. You can see that high level of the critical heat flux is the D equal 10. D equal 10. There many dimple. So I want to show you the moving picture of the bubble motion. Here. Just a moment. Here. There presence of the bubble. This result is D equal 20. And this is the D equal 10. Zero moment bubble. And to enhance the heat flux. Very simple reason. As mentioned previously, the zero moment dimple on the surface, because the diamond particle installed is a distance is 10 millimeter. So based on this heat flux, the D equal 10, this is maximum heat flux. D equal 30 millimeter. This is the critical heat flux a little bit low than the result of the D equal 10. Throughout the experimental result, I'd like to show the summary. Diamond particles successfully bonded in the surface underwater explorer and ahead to each other without gap. Boring of the DPC surface in the Enquiries compared with the smooth surface due to the higher emission density. And the boring heat transfer is promoted by the diamond particle property of the heating surface. Boring heat flux increasing with increasing particle adhesion density and the corresponding critical heat flux enhanced of the wall surface superheating region. Both increase in the critical heat flux and the suspension of the wall superheat on the DPC surface are mainly due to the increasing effective surface area of the heat transfer. DPC surface show the better enhanced due to the fine thin action, high thermal density, conductivity, load resistance of the surface with a diamond coating surface. Thank you very much for your attention.